speak to us about audio sampling with MicroPython. Over to you.
Hi there. Well, thanks for turning up for probably one of the last sessions of the conference. My name's Alan Christie, and as we've said, I'm talking about creating a real-time audio sampling application using the PyBoard, which is this is in its case, but it's a tiny little hardware device, and MicroPython that runs basically on bare metal. Maybe I need to switch the pointer on. There you go. So I won't go into an awful lot of background. I've been writing software for a very long time. Basically, I'm a hardware electronics engineer who's evolved into writing software, as I suppose everybody does nowadays. But that's my computer when I first started. It's 1,000 bytes of RAM, which was fantastic at the time. For £100 was absolutely brilliant. I think the machine I've got at home at the moment is something like 32 million times as much memory as that, and probably costs about nearly as much in terms of expense to get it. And also when I was developing software, audio was carried around in your pocket on a little plastic box that you could basically play in your ear, so that was pretty cool stuff at the time as well. But in this session we're going to be looking at something that was brought to me as a challenge, which was somebody brought along to a meetup with a little cuddly toy that you spoke to and it spoke back to you, you know, an echo thing, and he said, well, you're a software and hardware engineer, you should be able to do something like that. So it was quite a challenge, first of all finding the hardware to do it, and this board is pretty cool because it comes with all the bits and pieces. So we'll be looking at creating an audio recording and playback application. This is really for beginners. There's no real highbrow magic Python stuff going on here. It's just a really cool app on a very limited piece of hardware. So we'll be looking at MicroPython briefly. We'll be looking at the PyBoard again, which is just a tiny little device, and the audio skin, which is a plugin that gives you a microphone and a loudspeaker. So MicroPython is a very lean implementation of Python, a few hundred bytes, but it's really optimized for microcontrollers and for hardware and embedded systems. Stop thinking about trying to use complex libraries with it, because you're unlikely to be able to find them that run on the board. And remember, the board is a very limited device in terms of power and memory. So the board that's inside the case looks something like this, and gives you access to a couple of switches which you can program, reset the device. It's got a number of LEDs, and it's got tons of I/O around the edge of the board, which come out of jumpers. It's fairly limited in terms of memory. You've only got a few 100K of RAM, usable less than 100K when your code is running, and you're on a relatively low-powered device. But you do have access to some really cool hardware components. There's onboard digital I/O, for example. And in order to use Python on the board, it's flashed on the device, and you simply just have to import PYB, which is import the PyBoard software. The audio skin is a plugin which just sits on top of the device and gives you, as I said, a loudspeaker with a small power amplifier and a built-in microphone. But be prepared, because it comes in bits. So this is actually quite challenging. If you're not a hardware, if you don't have a very decent soldering iron, this is going to be a bit of a challenge, unfortunately. So there's some assembly required. What we're going to be doing is recording speech, so I guess a very basic understanding of what speech is in order to accomplish that task would be valuable. We're all familiar with the sort of time domain representation that you see with any audio recording application, which is just time and amplitude, and what we've got here is some speech with a time and frequency access, so we can see the frequency components of speech. And they're vitally important because we're going to be recording this, and we need to know what frequency range we need to sample, we need to record at. Hi-fi audio is typically 14 kilohertz. You can hear above that, but typically that would be considered fairly decent hi-fi piece of equipment. And over the phone, it's very limited bandwidth with about 3 to 4 kilohertz. So that's considered all the bandwidth you need to capture human speech, but it does extend beyond 4 kilohertz. So when we go from audio to digital inside a device, obviously we have got to capture the signal at regular intervals, and this is where the real-time aspect comes in. So at some point we have to record and sample data at a very specific time. Sampling frequency is important, so back to our frequency domain signal. If we're going to capture 4 kilohertz, then basic sampling theory tells us that we've got to be sampling at least 8 kilohertz or above in order to capture all of the components. In this particular example, I'm capturing data at less than twice the speed of the signal that's arriving. As you can see, that effectively aliases to what is effectively a lower frequency signal. So if we want to record 4 kilohertz audio, we've got to sample at least at 8 kilohertz. The board gives us 8 or 12 bits of sampling resolution. The number of bits is important. This is fairly obvious when you think about it. The more bits you've got, the more accurate your sample is. Quantization error is the error between your sampled digit and the actual analog signal. So the faster you're sampling, the better, but the more bits you've got reduces the quantization error. For those who don't know what a CD is, a compact disc, these are rapidly disappearing, I think, but I wish I'd brought one along, or even an audio cassette, which some kids are amazed at. It's sad when components of your life disappear and everybody just forgets about them, and you think that they were cool at the time. Never mind. Okay, so compact disc audio is typically 16 bits and sampled at 44 kilohertz. And words are typically 300 to 500 milliseconds long. So all of this information tells us roughly the speed at what we need to sample, roughly how many bits we want, and how much memory we're going to need to record words. So how do we record on this board? Well, we simply create an ADC object. We have two methods. We can call a timed function that just goes away, records audio for us and then stops, or we can access the audio manually with a read function. So effectively we create an ADC object and connect it to the right port. If we're just going to do a raw recording with no control, hand it over to the operating system, then we can call a read timed method, which is given a timer, and we basically just tell it at the frequency at which we want to collect audio. So when we call the read timed, that will block until the byte buffer that you've supplied it has been filled up at a rate of 6,000 samples per second, which is great, but you have no control. You have to start the recording, step back and wait. So in a real-time application where you want some interaction, you really want to be handling the read yourself in what would be considered an interrupt service routine. And in that case, you can simply take your ADC object and do a read on it. But if you're doing this, of course, you have to read at a precise rate if you're going to play it back. So we've got our audio. Let's assume we can get our audio into our board. We now need to play it back. Again, quite simple with a PyBoard. You've got two components. You've got a potentiometer, a volume control, and you've got the digital to analog converter. So you can simply set the volume of the output using a PyBoard I2C bus call, and then in this particular example I'm handing over to the operating system to say write out my digital data in one go, and I supply it with the buffer where my data is stored, and again I supply the sampling frequency that I want to play back at. Again, this is a blocked method, so if I have audio in my board, I just point it to the buffer and sit back and the audio gets played out for me, which is cool if I don't want to have any interaction or anything more sophisticated. Again, you can also write manually to the DAC. In this particular application, everything has to be real time. I've got no control over how long I want to sit around and take samples. I have to take them once every 1/8,000th of a second. If I don't, the audio playback is going to be corrupted. It's just going to sound awful. So you have to have some mechanism that allows you to record data. The other thing is that you were doing some audio processing, so we're capturing samples and putting them on the board in memory. We have to be sure that we aren't going to breach that 1/8,000th of a second. So there are two ways you can do this on the PyBoard. They provide you with basic pins that you can set to high or low. So I can set a pin to a logic 1 or a logic 0, and if I have an oscilloscope, then I can see a strobe, and we'll see that in a moment. Or you can use a timer object. So you can just set the timer object at the start of your code and read it at the end. I happen to use an oscilloscope, and here's an example of the pin strobing. So I enter my interrupt service routine at this point, and I exit at that point. So that's where all my work is taking place, and there's the next interrupt service routine taking place. And this happens to be recording at, I think, 6 kilohertz. So the distance between those vertical edges is about 167 microseconds. So that's my hard limit. So I only have 167 microseconds to do all of my work, and it's surprisingly short, considering that just reading the ADC takes 50 microseconds, which is about 2.5 of those little squares. So a lot of my time in my interrupt serve routine is just getting the data off the ADC. So I'm very limited in what I can do in real time. So my initial development setup, I create a timer, and I define a sampling frequency, and I have what is considered in the PyBoard to be a capture function, effectively interrupt service routine. So my timer at my programmed rate, 6 kilohertz, 8 kilohertz, will launch my function, at which point I have to do my work and then exit before the 167 microseconds is up. In this particular case, my capture function just has a pointer to a pre-allocated buffer. I do a read and I store the data. The PyBoard's quite small, so I can't have tens of seconds of audio. Surprisingly, it is very short. I've only got 100 kbytes, thereabouts. And once my data's captured, once I do some experiments, I just have to have a simple play routine that takes the address of the buffer, as we've seen before, and just writes that out at a defined rate. So I made some initial recordings with the PyBoard, and this is an 8 kilohertz recording of me just saying A, B, C. Which I think you'll all agree is pretty lousy. That's incredibly noisy background disturbance. So the noise in the device is probably caused by the non-professional hardware. I mean, this is not exactly a sort of professional piece of kit. You do have the ability to, obviously, because you can write out, you can play back pre-recorded audio. And when I've done that, effectively, it's clear that all of the noise is coming from the analog components on the input. But nevertheless, it's really quite noisy and constitutes more than, if this is a 12-bit recording, 8 or 9 bits of it are just consumed by this noise, which in silence regions is really painful. So reducing the noise, simple first effort is detecting when I think there's silence. Luckily, there's enough signal left over from the noise that I can make some estimates of when I think the silence occurs. So I just remember where the silence is, and when the recording is over, I go back and reset those to an approximation. So what's going on in the background is I'm writing to a frame, an array of data, but I'm breaking it into frames typically of a few hundred milliseconds. So as the recording takes place, as we've got here, I'm actually analysing as I go, using an approximation of what I think silence is at the start of recording. So that tells me roughly what silence sounds like. So using that, I can mark areas of this buffer that I think constitute 100 milliseconds of silence. And once I've done that, obviously it's easy to go back once the recording's done and write to those areas of the buffer and clear them down. Now, even though the noise is present in the speech, because you've got a higher signal, it's not as obvious. So I have a recording here with the noise reduced algorithm. Compared to the original. And all of that is just through this simple algorithm here. I'll skip that bit. So that doesn't give me my real-time application because I don't want to press a button to make recordings, so I want this to be real-time. So I need some speech detection as well. And the way I do that is that when I'm recording, I'm using a very small buffer in a circular fashion to record audio, but because I know the silence level, I can make an estimate of whether someone started speaking. So that little buffer acts as a recording trigger. Once I start speaking, I then switch to the main buffer and record until that's full. And in this way, I don't have to press a button to speak, it's just listening all the time, and as soon as I speak, it records and then plays back my audio. I also added an end of speech detection, and simply, a bit like the silence detector, I go through the buffer remembering where frames of silence are as I'm recording, and as soon as I reach what I consider a period of silence that's long enough to indicate end of speech, I can stop the recording prematurely. Because ultimately I want a very long buffer, but I don't want to, if somebody just says a short word, I don't want to record for 10 seconds. Once they finish speaking, I want to play back. So the end of speech detection allows me to stop recording early and play that back. And you can respond to user switch events by simply putting in a callback or a handler function. So I can use the user button to put the system on hold so that when I'm talking at a demo, it doesn't keep popping up and saying hello. And I can drive LEDs quite simply using the PyBoard LED objects. There are 4 of them. The blue one allows me to give an intensity level, so I can throb the blue one if I want, but I've got 4 LEDs for control, and I use that for an indication that it's listening, it's on hold, and it's recording. And I can record to an SD card, nothing particularly special other than you know that an SD card is plugged in MicroPython if there's a /SD in your filing system. And putting it all together is a block diagram here where I have my recording timer that is triggering my capture function, which is continuously listening to this small speech buffer and then switching to the main speech buffer when it hears me speak, and then control variables switch to the attenuation algorithm, which erases areas of silence, and then I have a playback function which just writes to the DAC. A few other components on this board here, but I haven't got time to go through all of them, other than probably try and end with a well-advised, non-advised example of not doing a live demonstration. So, plug that in. Unfortunately, the PyBoard doesn't come with an onboard power supply, so you have to have an external power supply. So I've got my LED flashing now, which is telling me that it's on hold, so let's switch to record. Okay, Alan, don't do live demonstrations. Okay, so you'll notice there that of course I'm playing back at a different frequency that I'm recording, but now all I need is a fluffy toy to put it in and some marketing guy who will tell me, too late Alan, it's already done. So, okay.
Fantastic, thank you very much. Yeah, I think we have a few minutes for questions. So, yeah, are there any questions in the audience? One right at the back and then one just in front. Okay.
The code and the slides are all on GitHub if anybody wants to go and look at it, by the way. Hi there.
My main question is, what's the cost of the board in terms of money?
Yeah, it's a tiny board, but it's not the most cost effective. I think the board itself is something like £35. The case probably costs you another £10. The audio skin probably costs you another £10. It's not the cheapest way into audio, but one of the benefits of the PyBoard is this audio skin is well designed. It's a nice integrated unit. I thought about using the Raspberry Pi, but it's too bulky, consumes too much power, and this was just about as much hardware as I needed to get my job done.
Could you do filtering, like, so for example, to remove the noise, you could do a low pass filter maybe, and another kind of filtering, and what is the performance of doing that in MicroPython?
Yeah, so very good question. My background, by the way, is I've spent a lot of time building speech recognizers in the dim and distant past. So in military aircraft and on cars. So there you have the benefit of you have the hardware that you're using, you've designed for the job. This is very, very limited hardware. So you can do digital filtering, but you can't do that in the interrupt service routine, because the interrupt service routine, you've got very limited time in Python, but also you can't use floating point precision. So any algorithm you want, you have to run outside of the interrupt service routine. And the board doesn't have an awful lot of math libraries built in. So unfortunately, that level of digital filtering is sort of out of bounds for this hardware. But yeah.
Thanks for the talk. My question is, how strongly linked is MicroPython to the PyBoard? As in, like, you give your like literal toy example, but if you actually wanted to do that, is there like hardware that you could distribute your product on?
Yes, there is. There are other hardware platforms. MicroPython and the PyBoard are completely independent. The PyBoard, I think, was designed by the guy who made MicroPython just as a reference hardware platform. But there are other very tiny boards with just microcontrollers on it that will run the MicroPython on it, but I haven't tried that yet. Yeah.
Any other questions? No, it doesn't look like it. Oh, sorry, there is one. Yeah, we've got time.
Sorry if I missed this when I was taking a photo a second ago. Did you say that it will or won't work on the microbit? Is there anything missing or extra that would make it better or worse?
I don't know the microbit very well. If it runs MicroPython, your only problem are the drivers for the hardware. So do you have a DAC, a digital analog converter, or an ADC?
Probably. I have no idea what the resolution is though.
Yeah. Yeah, so this, interestingly, you can, because it's so noisy, I had to revert to 8 bits. So you don't need an awful lot of digital resolution for this to work. I think it's all down to the hardware that's on the microbit. I don't know how powerful that device is. This is running at 168 megahertz, I think, is its fastest speed. I have to do that to do the simple processing that I'm doing within 167 microseconds or less at 8 kilohertz.
Okay. Any others? No, I think that's okay. Well, that's fantastic talk. Thank you very much.
Okay.
And yeah. Thank you.